Have you ever wondered how much does a teaspoonful of neutron star material weigh? Well, let's embark on a cosmic journey to uncover this mind-boggling fact. Neutron stars, these celestial bodies, are among the most dense objects in the universe. Their unique properties and extreme conditions lead to some truly astonishing and mind-twisting facts that stretch the limits of our imagination. So, buckle up as we dive deep into the cosmic world of neutron stars. For starters, what exactly is a neutron star? Well, let's take a cosmic journey to understand this celestial body. A neutron star is the compressed core that remains after a massive star exhausts its nuclear fuel and explodes as a supernova. Picture a star about 5 to 20 times the size of our sun, burning bright and furious until it can't sustain its own weight. This leads to a dramatic explosion, and what's left is a core incredibly dense and mostly composed of neutrons. Neutrons, you ask? Yes, indeed. These subatomic particles, which reside in the nucleus of an atom alongside protons, are the building blocks of a neutron star. Now, imagine the force it takes to squeeze a star, which in its prime was millions of kilometers in diameter, into a sphere with a diameter of about 20 kilometers. That's comparable to the size of a small city. It's like taking a mountain and compressing it into a marble. This extreme compression is what gives neutron stars their name and their unique properties. But how dense are we talking about here? To give you an idea, if you could somehow take a sugar cube-sized chunk of a neutron star, it would weigh as much as Mount Everest. This level of density is simply unfathomable on Earth. Neutron stars are not just dense, but also incredibly hot. The temperature inside a newly formed neutron star reaches 1,000,000 degrees Celsius, which is hotter than the core of the sun. This celestial object, born from the fiery death of massive stars, is one of the most extreme and fascinating objects in the universe. Their formation, structure, and properties offer a window into the laws of physics under the most extreme conditions. Now that we know what a neutron star is, let's delve into its fascinating properties. Intriguingly, neutron stars hold some properties that are out of this world, quite literally. These celestial bodies, born from the supernova explosion of a massive star, are among the smallest and densest stars known to exist in the universe. Imagine a star with a mass greater than our sun, but compressed into a sphere only about 20 kilometers in diameter. That's roughly the size of a city. The incredible density of a neutron star is what makes it truly unique. Picture this. Just a sugar cube-sized amount of neutron star material would weigh as much as a mountain, around 1,000,000,000 tons. This insane density is due to the composition of neutron stars. They're primarily made up of neutrons, hence the name, packed so tightly that the atoms themselves collapse. The electrons and protons that once roamed freely within the atoms are squeezed together, forming additional neutrons and leaving behind a dense core of neutron-rich matter. Now this is where it gets even more incredible. The outer layer of a neutron star is 1,000,000,000 times stronger than steel, yet just a centimeter deep. Beneath this layer, the density increases rapidly, leading to a core that's so dense, a single teaspoon of it would weigh about 6 billion tons. That's the same as the combined weight of every human on Earth. The immense gravity of a neutron star also plays a role in its unique properties. The gravity is so strong that it warps the space-time around it, causing what we call gravitational lensing. This means, if you were to hover above a neutron star, you could see more than half of its surface at once, due to the bending of light around the star. That's a lot to take in, isn't it? But it's these properties that make our fact for the day possible. So, how much does a teaspoonful of neutron star material weigh? Brace yourselves for the answer. Hold on to your seats, folks, because the weight of a mere teaspoonful of neutron star material is a staggering 6 billion tons. Yes, you heard that right. 6 billion tons. That's billion with a B. To give you a sense of just how massive that is, let's compare it to something a bit more familiar. Imagine, if you will, every car on the planet. Every sedan, every truck, every sports car, every minivan. Now picture them all lined up, bumper to bumper, stretching on for miles and miles. The combined weight of every car on Earth is approximately 1.5 billion tons. And yet, that's not even close to the weight of our teaspoonful of neutron star material. In fact, you'd have to multiply the total weight of all the cars in the world by 4 to match the weight of a single teaspoonful of neutron star stuff. It's a testament to the mind-boggling density of these stellar remnants. But let's not stop there. If we were to compare our teaspoonful to the Great Pyramid of Giza, one of the heaviest structures ever built by human hands, we'd find that it would take more than 1,000,000 Great Pyramids to equal the weight of a teaspoonful of neutron star material. That's a pyramid for every person in the city of Chicago, with plenty to spare. And if we took all the humans on Earth, all 7.5 billion of us, and put us on a scale, we'd still fall short. We'd need to clone the entire human population almost 800 times over to match the weight of our teaspoonful. It's hard to wrap your head around, isn't it? But that's the magic of our universe. What might be the implications and consequences of such a heavy material? Let's start with gravity. The intense mass packed into a minuscule volume creates an extreme gravitational field. To give you an idea, if you were to get close to a neutron star, say within 1,000 kilometers, the gravitational pull would be so strong that it would accelerate your body to about 1,000,000 kilometers per hour in a split second. That's faster than any spacecraft man has ever created. Now, gravity doesn't just pull on matter, it also warps time. Einstein's theory of relativity tells us that the stronger the gravity, the slower time passes. So near a neutron star, your wristwatch would tick slower compared to a watch far away. This time dilation effect, as it's called, is not just a science fiction trope. It's real, and neutron stars are one of the few places in the universe where it can be significantly observed. This leads us to another interesting ramification. When we talk about a teaspoon of neutron star material, we're not just talking about a heavyweight. We're dealing with an object that quite literally bends the fabric of space and time around it. This knowledge of neutron stars and their extreme properties is not just a curiosity. It's a window into understanding the fundamental laws of our universe. It helps us explore the limits of matter under extreme conditions, the nature of gravity, and the fabric of space-time itself. These insights are invaluable in astronomy, physics, and cosmology. They help us to predict the behavior of other celestial bodies, understand the life cycles of stars, and even provide clues about the Big Bang and the origin of the universe. So while a teaspoonful of neutron star material might be impossible to lift, it certainly lifts our understanding of the cosmos. In the grand scheme of things, these facts remind us just how vast and mysterious our universe is. We've seen that neutron stars are not your everyday stars. These compact celestial bodies are the remnants of massive stars that have undergone a supernova explosion. They are incredibly dense, with a mass of about 1.4 times that of our Sun, yet they have a radius of only about 6 miles. We've also delved into the mind-boggling weight of a teaspoonful of neutron star material, a seemingly insignificant amount that would weigh about 6 billion tons here on Earth. To put that into perspective, that's about the same as 1 million Eiffel Towers. But what's truly fascinating about this is not just the sheer weight of this material, but also the implications and consequences it has for our understanding of the universe. It underscores the extreme conditions that exist elsewhere in the cosmos, far removed from our earthly experiences. These facts not only broaden our knowledge of the universe, but also spark our curiosity and sense of wonder. They challenge us to keep questioning, keep learning, and keep pushing the boundaries of our understanding. Next time you use a teaspoon, remember that in a different context, it could weigh billions of tons. Stay curious and keep exploring the wonders of our universe.